Good morning or afternoon, I guess, everyone. Welcome to today's presentation from Carbon Leadership Forum Chicago. I've got Scott Farbman here today from Database Plus, who's going to be presenting some research that he and his company have done recently on sort of all the carbon trade-offs that we make in our designs, specifically in high-rise building in Chicago. So he'll be looking at, if you're looking at a glazing system, is that third pane of glass in a triple glaze system going to be worth it? Is that upfront carbon impact offset by the operational savings? And similar for refrigerants, is a more efficient HVAC system worth that those emissions from refrigerants in that system? So yeah, some interesting questions, definitely some surprises along the way. I kind of got the sneak preview of this presentation, and yeah, definitely some interesting results. And I think there'll be a lot of good stuff to talk about as we go through. So anyone who's on the call, if you do have questions along the way, feel free to unmute yourself and interrupt Scott. He'll be happy to get some conversation going as we go. So yeah, go ahead, Scott. So yeah, this is hosted by Carbon Leadership Forum Chicago Hub. We're basically a group of folks in the built, AEC industries who are working on the challenge of embodied carbon, of that upfront carbon footprint of our buildings. We host events every couple months throughout the year. Speakers presenting research like this, or sometimes do more interactive discussions, and basically just all of us are trying to learn more about this and figure out the best way forward. So please join us. I've got actually on the next slide, I will send out these links as well, but our website, our LinkedIn, I'll put a link to those in the chat, but we will post event recordings, including this one, on the website. And you can, if you signed up for this, I've got your email address, and we'll let you know about future events, but you can also follow the calendar on the website or follow us on LinkedIn to be in touch. And yeah, again, any embodied carbon topics that you want to discuss, or you'd like to see see a speaker on, definitely get in touch and we'll try to get something set up. So yeah, with that, I'll hand it over to Scott to introduce himself and kick this off.
All right, thanks everyone. Thanks for having me. I'm really happy to be here and to talk a little bit about some of the research that we are doing internally. And just to start things off a little bit, on DBHMS and Database Plus, we are headquarters in Chicago. I think many of you are probably familiar with us, but we are, building and consulting and designing all over the US. And we have a handful of small offices starting to expand across the country as well. So Grand Rapids is where our commissioning group is headquartered out of. We have a handful of folks on the East Coast in Philadelphia and Boston. And then we just recently hired a couple people down in San Antonio. So we've got a good presence in Texas as well. And who we are, so DBHMS is traditionally a MEP design firm, mechanical, electrical, plumbing design, fire protection, lighting, etc. And then as part of the DBHMS group, we have our commissioning folks as well. And, it started off as systems commissioning with what LEED would require from fundamental and enhanced, but it's expanded quite a bit now. Again, to kind of follow suit with LEED version 4, we offer building enclosure commissioning and monitoring-based commissioning and a handful of other services as well. Now some indoor air quality testing and verification to help out with all those LEED and well projects. So the commission group has expanded quite a bit. And then with Database Plus, it was originally our high performance studio, but we've rebranded ourselves and just came up on 2 years with a technically different name. And it has been going quite well. It is a studio focused on human-centered design support and is fully research and data-driven. So we really want to provide the best support to all designs and teams as possible. So on the high performance side, it consists of our energy modeling, our comfort modeling, CFD, some of this new carbon research that we're doing as well, smart building works, you name it, our high performance studio is looking at it. And then on sustainability, it is, the traditional green building certifications, I would say LEED is still very much our bread and butter, but we have a couple of well projects now. We have done a few passive house projects. We have 3 under construction at the moment. And yeah, enterprise green communities, pretty much anything out there we're able to support on. And then me, I am traditionally and trained as an architect, but about 5 or 6 years ago, I decided to pivot over to the engineering side, and I get to kind of provide insights on both sides now, and it's been quite a great process and learning experience for me, building not only on my existing architectural knowledge, but being able to experience the engineering side of things every day has really given me unique insight, and I'm able to provide that insight on any project I'm involved in. Right now, a lot of my time is going towards innovation and research, but we still do have me working on some project management work and some LEED certifications and things like that. So there's my information. I'll post it again, and feel free to reach out. Today, I am going to be talking about carbon emissions. The first kind of half of the presentation is a bit more of an introduction to carbon emissions, both globally and at the building level scale. I'm going to talk about 2 of the studies we've done internally on refrigerants and window systems, and then I'll leave you with a few final thoughts, and hopefully we can have a good discussion after that. And my basic assumption is that a lot of you know about why we're talking about carbon dioxide, CO2, and some of the other greenhouse gases in the atmosphere and why it's important. So I'll go a little quicker through the first handful of slides so we can talk more about the study and have an open discussion afterwards. This is slightly out of date now that there's new data out there, but this is where, let me turn on my laser pointer. Are you able to see this on the screen? Okay. This is where we see operational energy use. So the energy used to heat, cool, light, ventilate, do all that good stuff in our buildings contributes 18% of the global greenhouse gas emissions. And that number is a little bit easier to wrap our hands around because we have utility bills. We know where a building's located, what the emissions is for that grid or due to the power plant and the energy mix. EPA publishes that data, I'm pretty sure every year. So when it comes to how much energy our buildings are using to power and condition, we know what that is. So where things get a little harder to break down, and 18 plus the remainder over here is where we typically get that 40% number. The built environment is responsible for 40% of the global emissions. It's coming from the building materials, the production of them, and the embodied carbon that's associated with all of them, with iron and steel, cement and concrete, and the rest of things here as well. And then, there's going to be some slices of transport associated with that as we bring things to the site, to the manufacturing plant, et cetera. So this is why, we're starting to look at the greenhouse gas emissions of the built environment, because it is a pretty substantial contributor. Now, where's things located on the built environment side, specifically in regards to our buildings and the buildings we design. So carbon emissions can be associated with every stage of a building's life cycle, and that's why we call it a life cycle assessment. So we have material extraction, getting it to the manufacturing plant, manufacturing that product, getting it to the construction site, constructing it. And then once the building's completed, things don't stop there. We all know about operational carbon. That's what I was talking about in the previous slide. So as we heat and cool our buildings, energy is used to do that. Carbon and other greenhouse gases emitted during that process of energy use. So we have energy used in the use stage. And then another thing that gets overlooked in the operational stages of things, it's not just about energy, it's also how often do you need to replace a material in your project? How often do you need to recharge your refrigerant system? All those considerations happen in this operation use stage as well. And then at the end of life, what happens to your building? A lot of us know the best thing you could do is reuse that existing structure, maybe repurpose it to a different use, but keep all those materials in the game still. Don't demo it. Don't bring brand new products and materials back to the site. Let's reuse as much as possible. And then at every stage, there's ways we can mitigate the carbon emissions and the greenhouse gas emissions to reduce the impact overall. So why are we looking at CO2 now and greenhouse gas emissions now? Again, this one's a little out of date with the new IPCC report. When we built this presentation, we were still talking about 2 degrees Celsius being the cap on global warming. Now everyone's getting on board with 1.5 degrees Celsius, and I think that's really where we need to be looking. And if anything, it just makes this thing right here, zero carbon, even more critical. So this graph is showing a couple pathways to keeping us under that global warming raise that we're trying to limit. If we continue on a business as usual path, we're going to blow ourselves out of the water, right? We're just going to keep using a bunch of energy. We're not going to be looking at renewable sources, and we're going to keep building with a ton of concrete, steel, and other non-natural materials. There's 2 emissions growth options where we really cut it down, but not as aggressively as we can. And you can see that those 2 options, where we would peak emissions in 2080 or peak emissions somewhere in between 2040 and 2050, would still not take us to that 2 degrees Celsius warming we're trying to fight against. Really, the only way we can get there, and this is what all the scientists are saying, is embracing zero carbon as quickly as possible. And the only way we could do that is if we fully evaluate the embodied carbon of our designs, we fully evaluate the operational carbon of our buildings, and also consider end of life when things get to that stage. So operational versus embodied. So I've already thrown those terms around a lot. I think most of you are familiar with operational versus embodied. And I wanted to kind of show 2 options. If we look at the life cycle assessment community and the standards that come out of Europe, the EN standards and the ISO standards, 60 years is really that standard life right now. And that's not to say that we shouldn't build our buildings longer than that. I think we should definitely try to build all of our buildings longer than 60 years, but 60 years is kind of the standard assessment period right now. So that's going to be the lifespan that I'm looking at and presenting on today. If we took a code compliant, business as usual building, when we look at total carbon emissions for that building, it's somewhere in between, 15 to 30% of that carbon emitted is from embodied upfront materials. And then the remainder, whether it's, 80, 70% is operational. So in this case, that is energy use specifically. So our typical buildings on our typical grid right now is still heavily dependent on the operational energy use being the biggest impactor to greenhouse gas emissions. Now, what if we flip the script a little bit and we look at our high performing buildings, something that has a more robust envelope? It's using more higher performing systems, both mechanically and otherwise, and also probably having some renewable energy on site. That relationship changes quite a bit. It's somewhere between 50 to 60% now being embodied carbon, which is why we're all starting to look at embodied carbon. We need to be more cognizant of the materials we're putting into our designs and that are ultimately built, not only what they are, but where they're coming from, and if there's other alternatives and options to doing what we were doing traditionally. So pie graph representation. Let's also look at a line graph representation. So again, we have our 60-year life cycle here. Let's say it was built in 2020 and it's going to operate to 2080. This first slice down here is a constant. It's our embodied carbon. It basically goes in on day 1 and it's going to last the entire time. It doesn't increase, it doesn't decrease over the time period because the building's built. Let's look at our business as usual option, iteration strategy. Each year we're using let's just say the same amount of energy, and it just adds up over time, over time, over time. It's a linear graph, right? So then we end up having, like a 3-to-2 relationship. That's kind of what I was showing on the pie graph. If we look at a high performing building where, same linear graph, same linear line, but it's just reduced because the building's operating more efficiently. So now we have that 50-to-50 ratio between embodied and high performance. Another thing to keep in mind, especially as we have CEJA written into legislation now, where the state of Illinois is supposed to decarbonize the grid over time by 2050. So let's say we still have that similarly performing building. It's going to continue to emit carbon and greenhouse gas emissions until the grid fully decarbonizes, and then it's going to be static from there. So, right now, this is really our best case scenario, and you can still see how in that best case scenario, embodied carbon is the biggest impactor to carbon emissions, which is why we need to continue to look at it as much as we can right now, because those buildings are going to be there for the next 60 plus years. And once they're built, we can't control what happens to the embodied carbon. So for whole building life cycle assessment, what is it? It is a lot. This graph is really hard to speak to because there's just so much going on. And instead of me reading off all the stages and kind of trying to explain what happens in a life cycle assessment, just know that there's an embodied impact side, which is up here, and it has everything to do with extraction of materials, transportation to the manufacturer. Spoke a lot about this already, and getting that product manufactured, then to the site and built, et cetera. And then we have our operational impacts down here, which is our energy and water. In this methodology is what most LCA practitioners are going to follow. It's this EN 15978 system boundary. It basically is trying to set an apples to apples comparison of any building we analyze. But within those analyses, there's a lot of variability because there's just so much information you need to fill into all these stages. So it takes a lot of work, it takes a lot of coordination, and that's why we're going to go on to this next slide here. So how's an LCA done? Well, the reference I'm making here is it's done very similarly to an energy model, and we're at DBHMS and Database Plus, we do a lot of energy models. Like, that's our bread and butter. So we're very familiar with the process, and LCA doesn't work any differently. You want to get in as early as possible. In schematic design, we could do some very high level assessments of the impact of embodied carbon. We could do shoebox models of the building, associate or attach kind of rules of thumb to performance of materials, and do some rules of thumb on quantities, and then start to make some decisions or start to inform some early phase decisions if there's different structural systems being compared, different window to wall ratios being compared. This is really where we can get in early and help. And then during DD, as things progress and we get more information, we get more details, we can run iterations and we can refine those models and assumptions. And then in construction documentation, we should have all the information we need to finalize the assessment. But then anything that happens after that, like I was saying, there's still a lot going on during use stage and end of life. We're still making best guesses. We don't know what's going to happen at the end of the life of the building, but we can give you different projections and educate on how that might be addressed later. And it might be helpful to have those structural systems designed to be deconstructed and reused. That's a pretty big bonus to things like mass timber and wood frames and things like that. So embodied carbon within a building. This is, let's just call it a generic building, because these percentages and relationships are going to vary based on the type of building. If it's a high rise, mid rise, low rise, different programming within the building, different systems within the building. So there's a lot of variability here, but at a 30,000 foot level, this is kind of generally what we're looking at for embodied carbon in a building. The structural systems predominantly have the biggest piece of pie in most of the buildings we design. And that's because they're traditionally concrete, steel, high carbon emission materials. I've seen structure go as much as 60, 70% of the pie. If it's a high rise and there's a lot of structure in a high rise, there's a lot of foundation work too. It's going to start to take more of the total carbon emissions of the building and total embodied carbon within the building. So from there, after we look at structure, envelope, finishes, MEP systems kind of share the remaining 50. And then you have a couple slivers here that talk about appliances, equipment, any of your site work, pavers, et cetera. That's what's remaining from the embodied carbon snapshot. And, we can't really control what the structure is, but we can advise on it. But two things that we at DBHMS and Database Plus can advise more aggressively on is MEP systems and envelope. So those are the two things I'm going to be jumping into now with some of the detailed research we've done. So MEP, if you've looked at the Carbon Leadership Forum research on MEP systems and interior finishes, I believe it was focused on office building retrofits or like office build outs. They had said that MEP could range anywhere from 10 to 20% of the total carbon emissions of that build out. And that's really just associated to equipment, like the physical equipment, the physical duct work, those actual materials. And, they say we're making a good guess on refrigerant, but we're not quite sure the total impact of refrigerant yet. But I'm going to show you what some of that impact could be. And again, this is just a case study, hypothetical situation, but I'll explain that in a minute. So I just talked about refrigerant, and this is why refrigerant is so important to take a look at. Our current R410A that we use on most systems in our buildings has a global warming potential of just over 2,000. So it's 2,000 times more impactful than just CO2 by itself. And that, could add up to be a lot. It depends what your system is. It depends how much refrigerant charge you have, and it depends how often that refrigerant leaks and you have to recharge it. And you'll see in a little bit how much that could add to the total carbon emissions of a building. And then down here, we have CO2 as a refrigerant. And I'll touch on this a little bit later with emerging technologies, but there are some systems that's starting to use CO2 as a refrigerant, and it's just a one-to-one global warming potential because we're always comparing back to carbon dioxide. So can we cut that down by 2,000 times? I think the answer is yes. I just don't quite know when it's going to be fully adopted. Okay, so what did we investigate? This is what we're calling kind of a typical multifamily building in Chicago that we would work on. This is actually modeled after a building that we're working on right now. It's 6 stories. It's about 100,000 square feet. And what we wanted to do was look at 4 commonly used HVAC systems and compare the total carbon emissions from those 4 choices against each other. Those 4 systems, so we looked at a 4-pipe fan coil unit, so central plant with chilled and hot water, going to indoor units, so it's all hydronic based. The only refrigerant in a 4-pipe fan coil is at the chiller, so it's a packaged unit with refrigerant. You're going to see that packaged units is what we're looking at for fan coil, PTAC, and water source heat pump. The biggest difference in variable refrigerant flow systems, VRF, is that refrigerant is flowing through the entire building. And all those refrigerant lines and connections are field installed. So there's a lot of refrigerant and it's going between outdoor units and indoor units throughout the entire building. So the boundary of refrigerant is significantly greater in a VRF than it is in either of the other commonly used systems. And you're going to see why there just is so much more variability with the VRF in terms of carbon emissions. And we'll get into that now. So refrigerant rates. we're looking at a couple things here. So we're looking at the total amount of refrigerant in the system. We're looking at how much that system leaks annually. And we looked at a low scenario and a high scenario to look at the variability there. And one area where we in the industry and the professionals and the researchers, the academics, et cetera, need to get better is really honing down on what this leakage rate is. Because if we look at VRF right here, on a low leakage scenario, it's 4% of its total refrigerant each year could leak. On the high end, it could be as much as 9%. That's a lot, and that's a big difference. And we don't really know what the rule of thumb is right now. So keep that in mind for next steps in terms of research and technology. And then the final piece here is end of life leakage. So when we decommission that piece of equipment, there's going to be some refrigerant lost. You can't recapture it all. And that is going to vary anywhere from 10 to 15% on our packaged units, or 10 to 20% on the VRF system. Again, because there's a lot of field installed refrigerant running through the entire building, it is tough to capture it all when you decommission it. So for the package units, it's quite a bit less on annual leakage, about half, so 2 to 4%, depending on that piece of equipment and how well it's maintained, manufactured, et cetera. So with that said, I do want to kind of give you my hypothesis going into this before we started, because I think it's interesting for you all to know what I was thinking before we ran the study and then what the results actually were. So after seeing this and seeing that VRF had a substantially higher leakage rate, I thought that the VRF system, though more efficient in operation, the embodied carbon impact from the sheer amount of refrigerant being replaced every year was going to result in a higher carbon footprint than the other three systems. And what we found was that wasn't necessarily true. So let me work through some of these graphs. I know there's a lot of information here. So this is total carbon emissions for the entire building across a 60-year life cycle. In blue here, we say this is the rest of the building. So this is the embodied carbon of the building. It's got the structure, it's got everything in there. And this is mostly a code compliant building because we don't often see like a really robust improved envelope unless it's a passive house project, but that's few and far between right now. We have refrigerant in gray here, and then we have operational energy in green. And what we're seeing here is we've got our low leakage rate scenario for all four systems, and we've got our high leakage rate scenario on all four systems. And we've got PTEC here on the left. So that's a packaged terminal air conditioner. That's our baseline system in multifamily. And it's pretty clear that that is the worst performer, mostly because it just isn't as efficient as some of these centralized systems. On our VRF, we've got some variability here. On the low end, the total emissions for the VRF is the highest performing. So let's assume the best leakage rate possible. It's going to be the best performer across the board. Now let's look at VRF on the high end. Let's assume the worst leakage rate scenario possible. It is the worst performer of these three. And I'm just going to ignore PTEC for now because I don't think it's not something we typically push nowadays. We're really looking at VRF, a water source heat pump, or a 2 or 4 pipe fan coil unit system. Water source heat pump, with these package units, you're not getting as much variability on refrigerant impact, 2 to 4%, or on the fan coil unit, it's actually quite best, 1 to 2.5%. And that's because it's got the least amount of refrigerant in the system. So what does this mean? It means a lot, and it means some stuff I can't even really consider right now. I think for me, 12% of the total carbon emissions being associated to refrigerant alone is really something we all need to keep an eye on. I'm not saying we need to stop designing and implementing VRF systems, but I think what this does tell me is that field fitted and installed installations need to be kept a really close eye on. I think we might need more QA QC on the field or in the field when it comes to VRF buildings to ensure that the leakage rate is as low as possible. This also tells me that with this emerging technology of different refrigerants, if we can continue to use VRF systems, but use a different refrigerant type, we're going to have the best performing system across the board, hands down, because it is, in terms of on the operational side, it uses the least amount of, the operational energy is the least amount for the VRF. Now, just kind of want to show you what I had already said. So on the low end, how things stack up, and on the high end, how things stack up. Some may argue that VRF on the high end, this might not be a significant difference, but I think it's something we need to consider. So what's on the horizons? And this is where I was going with different types of refrigerant. So up here on the top right, we have the Sandin heat pump water heater. This is using CO2 as a refrigerant. So if you remember, that's got a global warming potential of 1 instead of 2,000. So right off the bat, you're really limiting the impact the refrigerant has on this one system. Something else that's supposedly coming by the end of the year from Mitsubishi is called a hybrid VRF. These are being installed, designed and installed outside of the US, in the UK, Australia, and New Zealand, but they're not offered here yet. And what this system does is actually, it's quite great. So there's still refrigerant, but what they've done is limited the run of refrigerant from the outdoor unit to an indoor branch controller. So from there, things get converted into a hydronic system where hot and cold water, hot or chilled water, is then distributed throughout the entire building. So that refrigerant boundary that I showed a couple slides back is minimized closer to what a package unit might look like. So there's less refrigerant charge, and then there's less opportunity for leakage because you don't have all those fittings and connections and field installed lines throughout the entire building. So this is something that we're keeping a really close eye on. And as soon as it's available, it's going to be considered as an option when we're looking at VRF internally on any building, because we are seeing the variability in the sheer amount of impact that refrigerant can have on a VRF system, that 12% of your total emissions. How am I doing on time, Emily?
About 12:35, so
okay.
Good shape.
Okay, great. So that ends the refrigerant comparisons. I'm going to get into window to wall ratio and window systems now, and then I'll kind of do key takeaways for both at the end there. So envelope can range from 10 to 25% of your embodied carbon in a building, and that's quite a bit. So let's take a look at why that might be. So this is the greenhouse gas emissions of our typical enclosure assemblies that we would see in mid, high rise, in Chicago, and even across the US. This is an analysis that we did using Kaleidoscope, and that's a PAET tool, and it's quite nice. So if you haven't checked out Kaleidoscope, I would urge you to do so. And what we did is we plotted the typical system. So we've got our curtain wall on the top here. We've got a spandrel system. We've got a triple pane window system, and we've got a double pane window system. And then the way these things are broken down is cladding, in this case, would be the glass. Structure, in this case, would be the framing. And then you've got in your spandrel, of course, you've got some interior finishes and insulation here. I'm sorry, right here. And then in our solid wall assemblies, a precast concrete is down here. An insulated metal panel is over here. And then a brick veneer would be here. And I know you're saying we don't see brick veneer building that frequently, but there are some in the Chicago area that were built recently. One thing I want to point out is you can very quickly see that our curtain wall systems have the highest carbon footprint, and it's due to probably the sheer amount of aluminum in those systems. And then the glass itself does add almost a third of the impact there. And then down here below, we have our solid wall systems kind of in the the 7 to 10 range, insulated metal panel. is quite a bit more because it's got more aluminum, and it also has a lot of foam insulation in there too. So of the solid wall, this is our worst carbon footprint performer. And then one thing to keep in mind that is also interesting, not only is current wall the worst embodied carbon footprint, it's also the worst operational footprint too, because its R value isn't going to be as good as our solid wall options down here. So,
and then Scott, these numbers are per square foot, right?
yes, per 1 square foot of enclosure. Yeah, thank you. So what did we look at? We took the ASHRAE 90.1 prototypical high-rise building in Chicago, a little bit different than the refrigerant study, but we wanted to use this prototype. In this instance, it's a 10-story building, about 85,000 square feet. And the two things that we looked really closely at is what happens as window to ratio increases or decreases from 10 to, I believe, 70 or 80%. And then what happens as that window unit goes from a double or a triple pane, and what's the total impact from those decisions. Some of the other assumptions we made. So again, other than the windows ranging in area and performance, everything else was essentially a code compliant building. That's just kind of business as usual. So that's what we wanted to look at this period of time. So the envelope is prescriptive code compliant. The system is a PTAC system because that's the ASHRAE baseline system for multifamily. We assumed a reinforced concrete structure, and we weren't assuming any renewable energy on the project. Now, what was my hypothesis and what was my team's hypothesis? We thought that at certain percentages of window to wall area, the triple pane window wasn't going to be a net positive, that the extra embodied carbon of having that third pane of glass wasn't going to pay off the operational savings that window would provide at low window to wall ratios. Like I was thinking 20%, because that is a window to wall ratio that I would associate with a high performing building. And what we ended up seeing was, again, I was wrong. So I'm 0 for 2 on both of these studies in terms of hypothesis. So what are we looking at? Again, this is total carbon emissions for the whole building. Apologies, we don't have it broken down into different sectors here. So but this does include embodied carbon of the structural and other systems, and it's got operational energy in there as well. And the mustard colored bar graph is our double pane window, and our blue bar graph here is our triple pane window. So, and then I'm sorry, along the x-axis, we have increasing window to wall ratio from 10 to 70%. And what we found, even at 10% window to wall ratio, a triple pane window was going to provide a net positive to your total carbon emissions. Now, you might argue, is 0.9% worth considering? I don't know. I'll leave that up to the developers to decide. But interesting enough, even at the lowest ends of window to wall ratio, the triple pane window was going to yield positive results in terms of total carbon emissions. Now, as you add more glass to the building, obviously those savings become more substantial. So on the very high end at 70%, having a triple pane window versus a double pane window would yield a 5% total carbon emission saving across that 60-year life cycle. I thought
this was like super interesting, because we usually talk about how concrete is this huge emitter, right? That's a huge source of embodied carbon. But when we start looking at aluminum, then the window wall ratio matters so much, because aluminum is, while it's a much lighter material and we use less of it than concrete, the impact like per pound of aluminum is so huge.
Even with it having a high recycled rate too, like I think, we've probably gotten greenwashed along the way to think that aluminum is good because it's recycled, but it also, at the same time, its sheer impact is substantial. And even glass too, that third pane of glass could have a big impact depending on how much glass you have in the building. And I just wanted to show, if we're looking at a 60% window to wall rate, 60% window to wall ratio building, which I would consider business as usual in downtown Chicago. If you wanted to implement a triple pane window in that building would perform similarly to a double pane 45% window to wall ratio building. So just trying to put things in perspective, that triple pane in terms of performance can help you compare similarly to a less glazed building. So if the developer needs that much glass, then we could say, okay, you can have that much, but let me show you what happens when we take a look at a triple pane window instead.
And that sounds like a conversation that we're going to be having more and more as the energy codes get more stringent. So
yeah, and one thing I want to talk about here quickly is there's some limitations to the study, and there's things that we weren't able to quantify, or at least quantify yet in the study. So as you move to a triple pane window, that heat loss through the facade is going to be less, and you're going to need less perimeter heat because of that higher performing wall. So there's going to be some reduction not only in heating capacity on your equipment, but probably in ductwork and things like that, because you don't need to bring heat out to every window. So we weren't able to capture that, but that would further bolster the triple pane window savings. And then, go ahead.
No, I was just saying there's a couple of questions in the chat, so go ahead and finish that sentence, and then I'll ask them.
Yeah. And then the other two things to consider, thermal comfort too, hard to quantify, but that third pane of glass is going to make you feel more comfortable if you're sitting at the perimeter of the building. Again, hard to capture on a carbon assessment. And then finally, resiliency, that's a really big topic right now. During extreme weather events, that triple pane is going to work harder for you in extreme weather to keep people comfortable and the internal temperatures a bit more stable. All right, questions?
Yeah, Maria was asking if the window performance analysis was covering the 60-year lifespan, or if we were assuming some replacement of those windows, if that was accounted for.
Yeah, that's a great question. In this study, we did not assume a replacement. I know that you probably want to, and that might be more of a realistic situation, but this is assuming that window is going to sit in there and perform for 60 years. We want to do follow-up studies to this where we do look at a window replacement. Something that I found when we were doing research into windows was the IGUs themselves. If the seal breaks, you're kind of out of luck. You have to replace that whole system. You can't just replace the seal. So that's a limiting factor in window technology right now. And then I also learned that the glass, if it's been significantly heat treated or with the low E coating and stuff, they're having a really hard time recycling those pieces of glass at the end of life too. So there's some nuances to the window systems themselves that need to be further studied and considered that didn't quite make its way into this assessment.
And then Mark was asking too about different types of glazing systems. Sounds like you looked at aluminum, but there's fiberglass, there's PVC, wood, and frameless glazing systems out there. So yeah. Any thoughts on how that would impact the outcome?
Yeah, that's a great question. Keen eye, Mark. Willie, let's just go back to this slide. So I think, the reason we only looked at aluminum is because that's what's being used most frequently in these buildings. I think there's still a pretty negative connotation of fiberglass and PVC because it doesn't look as nice in these high rises. But you're going to cut down significantly on this blue bar, and you're probably bringing your current wall performance much, much closer to the solid wall here. That is something else we would really, really like to take a look at. And I think fiberglass is probably the most reasonable next option. I would love to get a wood frame in there. It just, in a high rise doesn't seem like it's going to happen quite yet.
And then Mark also mentioned in the chat that not all triple panes are the same. Some would maybe use like a window film versus an actual extra physical pane of glass. So that's another also, potential difference.
And Mark, great question. So if you follow me on LinkedIn at all, you'll probably notice that anytime I see someone advertising a new window system, the first thing I ask is there an EPD for that system, an environmental product declaration? And they say no. So I mean, that's an area that we really need more information from and more data from. We don't have enough EPDs for window systems, so there is a lot of variability. I think that that thin middle pane, that new technology I mean, it's less glass, so it's going to have a lower embodied carbon footprint. That's probably the next step to take a look at, and I would love to do that as soon as I get my hands on an EPD from someone. Cool, great questions, Mark. This slide is meant to kind of just put things in perspective from the window to wall ratio study. I want to compare the three kind of common options I see most frequently. So 20% window to wall ratio, that's what I would refer to as a high performing building. If you are able to get that triple pane window in there, you're saving 1.6% total carbon. On our code building at 40% window to wall ratio, you're getting just north of a 3% total carbon savings. And then on our business as usual case, our 60% window to wall ratio, you're getting about 4.25% savings. So if carbon emissions ends up being a primary objective for any new building, we're going to want to look at what it will take to get triple pane units in there. So I'm going to start wrapping things up now and recap on what we learned today. Refrigerant can account for anywhere between 1.3% to about 12% of the overall carbon emissions of a building, and the results in even a larger percent of the embodied carbon of that building. So as we look more closely at embodied carbon, refrigerant is going to become even more critical. Setting refrigerant aside for now, MEP systems and MEP equipment contributes significantly to the use stage just due to its natural reoccurring replacement. So every 20 to 30 years, you have to replace your equipment. That's just going to add up with embodied carbon too. And I don't think that has been fully taken into account on a lot of LCAs so far. Now, when designing our facades and paying close attention to the amount of glazing and the glazing type is critical. Triple pane IGUs will be a net positive, ranging from 0.89% to 5% in total carbon emissions. And again, while also providing benefits to acoustics, resiliency, and thermal comfort. There's also opportunities to reduce equipment sizing and eliminate perimeter heating in those scenarios too, just as I had mentioned. And then finally, to piggyback off Mark Willie's great comments, we need more data. MEP equipment and window systems are still significantly lacking EPDs. We need to see more of that if we want to have more accurate and refined LCAs. It's really preventing us from doing the proper carbon accounting that we need to do in our buildings to get to where we want to be. And then some final thoughts. So it's essential that we understand everything that goes into our buildings. And that means all the materials and all the systems. We need to look at it all. LCA is the key analysis that it requires, that's required to demonstrate a low or zero carbon building and design. So there's a lot of people saying we're designing zero carbon buildings, but there's not a lot of backup to prove that. So if you want to design a low or zero carbon building, we need to look at an LCA for that design. If you want to play a role in mitigating carbon emissions or have a project with a low carbon footprint, these studies and analyses are imperative. And then finally, as the grid becomes more renewable, the importance on limiting embodied carbon will become even more critical. And I think that's why we all know embodied carbon is what we need to be focusing on right now. So hopefully this presentation helped steer you in the right direction. And we at Database Plus and DBHMS are really excited about doing more comparative analysis on this topic. So thank you. Here's my information. Feel free to reach out and let's have some conversations.
Yeah, definitely everyone feel free to unmute and jump in with any questions. Doug just asked a really interesting one in the chat. Just what's your thoughts? I feel like everything is a question of like, okay, what do you want to study next? Because this is really just just a beginning, and there's plenty of gaps in the data that's out there, and what we can look at in a simple study. But yeah, Doug is asking, what's your thought on what if we just delayed projects until the CO2 based refrigerants were available? What kind of impact do you think that would have?
Yeah, Doug, that's a really great question. I think it's something that needs to be considered during the design of every project. And Doug, you've worked with us a lot, so you've probably seen the table we show when we're comparing design options. And traditionally speaking, it looks at what's the first cost of that system? How tough is it to operate and maintain? How does it stack up in terms of operational energy? And then what's its life cycle in terms of costs too. So what we're doing is we're adding a final line in there that talks about total carbon emissions so that we can apples to apples compare all of our system options when we approach a building and design and the client. So I didn't really answer your question because it's really a tough one. I don't know what you do because I would say my personal opinion is to try and get as much hydronic systems out there as possible where applicable. So can we look at radiant heating and cooling? And can we limit the refrigerant to a packaged piece of equipment like a chiller instead of having refrigerant running through the entire building? That would be my suggestion. And then I think as soon as that hybrid VRF is available, we can reconsider what that looks like in our buildings in the US.
Yeah, and just real quick, and it's just about almost coming up to 1 o'clock, so we're happy to stay on and chat and answer more questions and discuss. But just wanted to drop those links to CLF that I mentioned earlier in the chat, and then also we're looking to schedule an event in November on the Structural Engineering 2050 Challenge. So look out for that coming up. And if you signed up for this, we've got your email address. We'll let you know about future events. And yeah, and for anyone who has to jump off, just want to say thanks again to Scott and Database Plus for putting this all together. And then I think there was one more question actually related to that SE 2050. CLF Global just recently issued a challenge to the MEP industry too, to eliminate embodied carbon in their systems. So that, equipment, refrigerants, and all of that. So
what are my
yeah, I
thoughts
don't know,
on that?
Scott, that's a little more your wheelhouse than mine. So
I like these commitments and I think they're helpful and beneficial, but I have some qualms with them because just like the structural one, we're going to have concrete somewhere. There's always going to be concrete. You can't fully eliminate that, and you're not going to have a carbon neutral or carbon positive design if you're isolating your assessment and consideration of just that one system. Just like with energy, we have to take trade-offs across systems. Otherwise, we'll never get to where we need to be. So similarly to the MEP 2040, you're never going to fully eliminate carbon from those systems. As we shift to electrification, we're going to have refrigerant in those pieces of equipment. It's all about minimizing and reducing, I think, not about eliminating, because let's try and be realistic here. And again, I'm all for those commitments, but I think until those firms are either A, doing life cycle assessments, or B, contributing to life cycle assessments, it's just like a pat on the back to sign on. You really need to do the work. Otherwise, you're just kind of jumping on the bandwagon and not contributing.
Hey, Scott. So the life cycle assessment and the EPDs there. So perspective wise, you do pose the question and you do alert that. I follow that, right, online all the time. The course of action to get it more widespread, the whole Red Rover, come over, right? Is the foundation for that to do it open source, so when someone does it, everyone else has access? I'm just wondering how to make it more widespread. Or Emily, maybe you have a better thought on this.
Emily, you can jump if you want.
Just on doing like having more manufacturers kind of do these LCAs in the first place. I mean, I think it's definitely a cycle where, you know, any of us in the design field have to be asking for it. And it's tough right now just because there is so little data out there that you can't really penalize someone for not having an LCA when it's not at all the norm. It's pretty exceptional. But we do need to be asking for it, need to, you know, phase into having it be the norm so we can require it and require improvements and you know, when we say require improvements, even have a baseline to base those off of. It's yeah, it's a tough point to start from just because it has not been normal at all. And even as operational energy has become such a focus, but we just got to be asking folks to do the work. And
I yield about 90 calls a day, not counting emails, right? And my requests for these has happened one time in two years.
wow.
I've brought it to many groups that I want it, right? And that certainly the counterparts, meaning framing in general, is missing it because I love enclosures. So I'm just looking for something to help spearhead that so that it's less arduous on all of us.
Yeah, I think the biggest hurdle right now, Mark, and it's more so for the smaller specialized manufacturers, is there's a substantial cost to getting an environmental product declaration. That's just a fact. And there's even more cost to having it third-party verified, which is what most people want to see. So until that gets addressed, you're going to have a lot of small specialized manufacturers having trouble doing that. I would love to see some grant or incentive money go to those manufacturers as means of the infrastructure bill or something like that to help.
Yeah, like it always comes back to public policy, right? Like in, you know, a couple of these states that have a buy clean policy, which does require EPDs for big ticket items like concrete and steel. And that allows governments to set a limit on carbon emissions from those products because they're getting the data to base a limit on. I don't know how many of those states who have that also have some kind of incentive or grant money for the smaller manufacturers to get that done, because it's definitely a way for, you know, a smaller one to compete.
I would love to see a panel discussion on how to create a pathway so that this is replicatable. And that comment you made, Scott, for the third party group doing this, I don't think people are aware of that. I think people are like, well, we just have to have this. Well, have to have what, right? And how does it come together? The staircase isn't even in their mindset yet, right? They don't see the ladder of how to get there. So all these points were great. This is the highlight of my day so far. Thank you all for putting this on.
My pleasure.
Yeah, thanks, Mark, for all your questions. Definitely, I know you said it was a rabbit hole, but that's kind of what we're all about, right?
And Mark, you're working in the wood world, right? And there's, you know, the blanket statement is that wood is better, but it depends where it comes from. Is it sustainably harvested? And then what happens at the end too, like if you're going to incinerate it, a lot of that sequestered carbon just goes back. So like there's all these blanket statements about what's better than what, but the truth is you can't really know what is until you do the analysis and you get the data. And we're just breaking into it now. I mean, we need more people to get on board. I think we need more transparency. Everyone loves to talk about transparency. We need more of it. And we need a program or something that supports all manufacturers to get these things produced. I think that would be critical.
And Scott, like you said, you know, your instincts on both of these questions turned out to be wrong. Yeah. So every little bit of data on this is like, okay, we're building up our ability to make those gut decisions. You know, it's getting easier and easier to get to the right hypothesis, the
Yeah,
more we know.
I love, I loved being wrong, which is funny to say.
Right. No, totally get it.
And I'm not I'm not the best building scientist. I'm not the best high performance consultant. Like I'm probably average at best. But if all of us who are average at best have similar rule of thumb thoughts, we're going in the wrong direction on some of these things. So it takes the data to prove it. And we're now in a world where we can start doing that stuff now. I mean, everyone talks about data-driven design, and we're able to do that finally. It's really important. Any other questions, Emily?
I didn't have anything else in the chat, but yeah, anyone else have questions, thoughts?
I will say, whoever is still out there, I don't know how many people are.
It looks like about half folks are still on. So.
Yeah, I think one thing that I'm learning about doing LCAs is the hardest part to getting the ball rolling is getting your material quantities. So how much concrete do you have on the building? How much steel, how much wood, et cetera. It is very, very hard to get that information. And anyone who's working on design that has any interest in trying to do this, it is really important to, in the very early stages, have some sort of workflow set up so you can get access to that information. I'm learning that that's like the most critical piece. Otherwise, it is literally like pulling teeth from people to try and get those material quantities. No one wants to do it. They'll say, look at my Revit model. And I'll say, how do I know that Revit model is done accurately? How do I know things aren't double counted? I need help doing that. So come up with a way to get those material quantities. If there's a budget estimator estimating things costs for the project, they probably know how much concrete they need to procure, probably know how much steel, et cetera. It's just all about connecting the dots early enough so you can get access to that information to do better analysis.
I would say, Scott, and as you pass that ball forward, when there's a change, that should be a verification change versus start from scratch and you don't know what you've been handed, right? So the formula has to be able to be manipulated, because we all know that there's a mistake, intentional or otherwise, right?
Yeah.
So perfect.
And even take, like you had said, changes if you're thinking about alternates and like the submittal process. Everything needs to be looked at full picture. Like you can't, Emily, I'm sure would agree a million times. In a perfect world, we'd have performance specs that says this thing needs to have at max X kg CO2e per unit of material. And we don't want anything above that, but we're not quite there yet. So when it comes to alternates and things like that, we need to pay even more attention if we want to make sure that we're getting the right things into the buildings.
Yeah, so I think the kind of thing like you're studying here is so important, because while we talk about the huge impact of concrete and cement, like there's really only so much we can do about having that on our buildings, right? Nothing else can do what concrete does. But in terms of what your envelope is made of, there's a lot more choices. And in terms of how much of that envelope is one material or another, a lot more choices. So
hopefully we start seeing less, glass boxes out there, but we're at the mercy of whoever pays us to design the buildings.
A couple of catchy hashtags in the chat. Hashtag more APD, not more glass. And the glass box.
Cool. Well, anyone who's still on, if you have any more questions or want to reach out, please feel free to email me here, and I'm happy to. Carbon's like all I think about nowadays, so I'm happy to talk about it at any point. So thanks for having me.
Yeah, thanks everyone for joining us.
All righty.
Thanks.